morning. What's up, Kyler? Everyone feeling strong? Feeling ready? Bit drowsy? I feel you. It took a while for me to get to sleep last night, and I am reaping the effects of that today, but it's all right. We're gonna make it through. Looks like it's supposed to be. I'm just realizing how super bright it is outside. Is it supposed to be super nice out? I hope so. Let's check. All right, what do we got? 51 right now. All right, that's yeah. All right, up to like 70. Not super warm, but I guess pretty sunny at least. That's nice. I'll take it. Can't complain. Oh, I'll complain though. The rest of the week's kind of cool though. That kind of sucks. It's not really supposed to get up over 70 throughout the rest of the week. All the way even into like next Monday. Damn. Oh well. Hey, I'll take sun. I'll take some sun. Get my tan. All right. Let's go ahead and get through the warm-up. So, number one, find the determinant of the matrix. So here's this matrix E. I want to find the determinant of E. So remember, we can write that in one of two ways. We can write determinant of E, or we can write E with almost looks like, you know, absolute value bars there. Either way. Okay, so first we take our main diagonal, 6 times -2, minus the product of the other diagonal, so minus 3 times -10. So -12 minus negative, so that would be plus 30. Should be positive 18 for the determinant. Okay, number two, if possible, use the determinant to find the inverse. So, why does it say if possible? Well, first we got to look at this determinant of 18. So remember, if the determinant is not 0, then the matrix E is not singular, which means that it does have an inverse. Remember, what singular means that the determinant is 0, right? And so basically what we conclude is if the determinant is 0, then that means that matrix has no inverse. All right, but this matrix's determinant is not 0, so we know that it does have an inverse, so we can actually find this. So let's find it. All right, so E inverse is 1 over the determinant Okay, so what we do, 6 and -2, switch places. 3 and negative 10, they stay where they are, but we just introduce another negative sign. So that would be negative negative 10, so positive 10, negative 3. Now let's do matrix scalar multiplication, where we multiply all this stuff by negative 118. So negative 2 over 18, 10 over 18, negative 3 over 18, and 6 over 18. And then now let's just simplify. Negative 2 over 18 is negative 1/9. 10 over 18, 5/9. Negative 3 over 18, negative 1/6. 6 over 18, 1/3. So that is the inverse of E. So keep in mind, what does it mean to be the inverse? Well, that means if we did matrix multiplication, if we did E times E inverse, we would end up at the identity matrix, right? The 2x2 identity matrix, 1, 0, 0, 1. Okay. Or if we did it the other way, E inverse times E, same thing. We'd end up at the identity matrix. So pretty nifty. Super neat. Just remembering a couple formulas. So first off, just the determinant formula. And then second off, the process for inverse. So and remember, this is the process for inverse of a 2x2 matrix specifically. 1 over the determinant, switch the spots of the main diagonal, and then on the other diagonal, keep them where they are, but introduce another negative sign. Or introduce a negative sign. All right. So that's how we do it for a 2x2 matrix, the determinant from number 1. But now let's find the determinant of a 3x3. All right, now it's a little bit different, a little bit more complicated, unfortunately. Okay, so let's say we have a matrix A. Here's our 3x3. Right, 3 rows, 3 columns. Okay, and so here's the formula. So remember, these bars just mean determinant. So determinant of A equals all this. Now, how is this built? Let me show you. So we first look at that first entry, A, and we get rid of the row and the column that is in, right? So so A goes here, right? That's why A is front here. And then if I cross out the row and cross out the column, look at what I have left. EFHI, that's exactly what's right here. Right? And these bars, again, mean determinant. Okay, now this is a 2x2. We know how to find the determinant of a 2x2. Okay, so we could do that. All right, and then we move over. So now we go to B. So we just kind of shift over 1. And same thing. I'm going to cross out the row and cross out the column. Oh, come on. Don't attach those together. All right, so I look at B, I put B there, and I cross out the row, cross out the column. Well, look what I have left. DGFI, that's exactly what goes in this one. Okay, and lastly, so now if I move over to C and I cross out the row and cross out the column, I have DEGH. That's exactly what's right here. Okay, so that's where we get these, numbers from, or these entries. How does it decide? Well, whatever the coefficient is, A, B, or C, you cross out that row, cross out that column, and the stuff that's left, that's what goes inside of that 2x2. Now, a really key thing to note is that this is a minus sign. While all these other ones are positive, right? So this is plus C, this is just A. But for whatever B is, we're going to change the sign of it, right? We have a minus sign in front of that. Okay, that's just part of the formula, right? I don't really have a great explanation for that without trying to explain much higher level stuff. But it's just how it works out. All right. Do the methods always change for how the equation is? Will a 4x4 solve completely differently? No, actually, this is now the general form. So here, let me quickly. So let's say A, B, C, D, E, F, G, H, I, J, K, L. If I want this determinant, actually we would start in a similar way. So we would do A, cross out the row, cross out the column. Oh no. And then it would be determinant, or wait, actually. Oh, sorry, this isn't. L, M, N, O, P. There we go. I was like, wait, why isn't this working? All right, so we'd cross out the row, cross out the column. What would be left? F, G, H, J, K, L, N, O, P. And then minus B, cross out the row, cross out the column, cross out the row. So what's left? E, G, H, I, K, L, M, O, P, right, etc. And then I'd have C and D. But here's the problem. So this represents determinant of a 3x3, but in order to do the determinant of a 3x3, I would have to do this whole process, right? Because this is determinant of a 3x3. So it's kind of like you have to do the calculation within the calculation. And I would have to do a 3x3 determinant 4 times. I'd have to do it here, I'd have to do it here, I'd have to do it for the next 2 terms as well. So yes, it is the same thing. However, for each one size you go up, it becomes much, much harder. Because this determinant alone is doing this whole equation just once, right? And then doing this determinant is again doing this entire equation, and then we'd have 2 more like that as well. So this is now the process, but it becomes very hard once you're above a 3x3. How do you find the determinant again? What do you mean? Hold on. What do you mean? Of what? A 2x2? A 3x3? 2x2, we did this, right? 2x2 is multiply these minus multiply these. 3x3, I haven't shown you an example yet, but it's this whole thing. That's a 3x3 determinant. So let's see it in action. Find the determinant. Is the matrix singular? Does it have an inverse? All right, well, let's just first focus on the determinant. So the determinant of R equals, so I'm going to start with 2. Okay, and then I'm going to imagine if I cross out the row, cross out the column, what am I left with? I'm left with these 4 right here. 0, -1, 4, and 5. Actually, here, let me do this. Okay, cross out the row, cross out the column. Boom, boom. 0, -1, 4, 5. Okay, great. Okay, so now the next term, so I move over to -3, but in between there's a minus, so minus -3 and move this over. I cross out this row and this column, so what am I left with? 2, -1, 1, 5. Right? Plus C, what is C? It's 1. Okay. But then I'll cross out that row, that column. So plus 1 times the determinant of 2, 0, 1, 4. Okay, so I have to do 3 2x2 determinants. So the coefficient is 2. Doing this determinant, so 0 times 5 is 0, minus 4 times -1 is -4, so that's 0 plus 4. Minus -3, so plus 3. All right, this determinant, 2 times 5 is 10, minus 1 times -1 is -1, so minus negative, that's 10 plus 1. Plus, 1, whatever, I don't know if I need to write that. 2 times 4 is 8. 8 minus 1 times 0 is 0. Okay, so a little more simplifying. 0 plus 4 is 4. 10 plus 1 is 11. 8 minus 0 is 8. So 8 plus 33 plus 8. So 49. So just remember or think about, each of these is a 2x2 determinant. And so that just turns into using the 2x2 determinant formula that we learned last time that we did on the warm-up. And then we just end up doing the actual calculations of multiplying and adding stuff together. Okay, so the question doesn't just ask what is the determinant. It asks, is the matrix singular? This determinant's not 0, so it's not singular. Does it have an inverse? Yes, it does have an inverse. Right? If it were singular, if we did get 0 for the determinant, we would say yes, it's singular, which means there is no inverse. But this determinant is 49, which means it is not singular, so that it does have an inverse. All right, let's try this again. All right. So we have a matrix W. Find the determinant. Is it singular? Does it have an inverse? So we start with our first number. So determinant of W is the first coefficient, 1. And then we look at, all right, cross out the row, the column. What do we have? So the 2 by 2 is -1, -3, 3, 1. All right, now I move everything over. So now I'm looking at 3. And why does it always do this? Okay, I want to cross out that row, that column. Now remember, for the second one, it's minus. We put a minus sign here. That's just part of the formula. So -3, -3, -3, 2, 1. Shift over to now look at that last column from the top row, 2. Cross out that row, that column. So +2, -3, -1, 2, 3. Okay, now let's do the math. -1 times 1 is -1. Minus 3 times -3, that's -9. So minus negative, so +9. Minus 3. -3 times 1, -3. Minus 2 times -3 is -6. So minus negative plus 6. Plus 2. -3 times 3 is -9. Minus 2 times -1 is -2. Minus negative turns into +2. So 1 times -1 plus 9 is 8. -3 plus 6 is 3. -9 plus 2 is -7. So 8 minus 9 minus 14. -1 minus 14 equals -15. So that is not singular. And because we didn't get 0 here, so not singular means that it does have an inverse. Okay, hopefully this makes sense. Again, it's like a lot of matrix stuff that we do. None of this is hard calculations. It's just very easy to get mixed up, especially in these steps. All of these steps, the formula is this product minus this product minus this product minus this product. All of these ended up changing to a plus sign, but that's only because our second number ended up being negative. We had -1 minus -9, -3 minus -6, -9 minus -2. But it's just super easy to mess up those negative signs, so just be very, very careful. Okay, but I hope you can see the pattern. I hope that makes sense of what, how we go about creating this by looking at the number, crossing out the row and the column, and then just remembering this middle one is a minus sign between the terms. Can you show the 3 by 3? Yep. There you go, Jacob. Let me know when you're good. No. No, 2 by 2. The determinant is just A times D minus B times C. It's purely just subtracting the two products. You're sort of mixing up the formula for inverse, right? Which inverse we did in that warm-up. So let me just bring this down so we can compare. All right, so like, yeah, for the formula for inverse, what happens is A and D switch places, and then B and C we times by a negative. So -10 becomes +10, 3 becomes -3. All right, so you're sort of mixing up. So this is the process we do for inverse, and we use the determinant in the inverse, but yeah, 2 by 2 matrix is just purely multiply these two numbers together minus multiply these two numbers together. Yes, sir. Good question. Easy to mix up. Okay. Let's go ahead and do one more. Oh, did I skip this one? Oops. Okay. The determinant of B. All right, well, this is going to be pretty easy. So check it out. 0. Cross out that column. Cross out this row. So -2, 1, 2, -1. Minus, right, the formula says minus. So I shift this over. 2, and then determinant 3, 1, 3, negative 1. Plus, shift this over, cross out that column, negative 1, 3, negative 2, 3, 2. Now look at this first term. I should calculate this determinant, but look what happens after that. I just multiply it by 0. So I'm not even going to take the time to do this determinant because I know this whole entire term is just 0. So forget it. It's a waste of my time. All right, let me just move on to these other two. So negative 2. This determinant, so multiply 3 times negative 1 is negative 3. Minus 3 times 1, which is 3. Plus negative 1, so I'm just going to write that as minus 1. Right. 3 times 2 is 6. Minus 3 times negative 2 is negative 6. So minus negative 6. That's one of those terms where this turns into 6 plus 6 then. So negative 3 minus 3 is negative 6. 6 plus 6 is 12. So I have my two negatives over here. Negative 2, negative 6 is positive 12 minus 1 times 12. So 12 minus 12. My determinant ends up being 0. That's interesting, not only just because it's 0, but that affects the rest of our problem. Because remember, if we get a determinant of 0, that means that B is a singular matrix. And if B is a singular matrix, what that means is that B has no inverse. Okay, so even if I went through trying to find an inverse for B, it would be impossible to do. Because it turns out there's a relationship between determinant and the ability to find the inverse. And what that is if we get 0 for the determinant, that must mean that there is no inverse for that matrix. Right? And we call it singular. All right, but it's just a matter of getting the pattern down and recognizing this is the process that we go through of get rid of the column, get rid of the row, going through and doing it. Sometimes it might work out that a lot of stuff cancels itself out, like that 0, or maybe determinants of this of one of these 2x2s ends up being 0. So we can hope for that, but who knows? Okay, how's that formula seeming? Yeah, definitely weird. Are there you dorks in physics? You guys talk about vectors? Wait, is that yep to the vectors or yep to the physics, Jacob? Sometimes. Well, interestingly enough, well, have you talked about what's called a cross product? You probably know if you had. But cross product is basically, it's just a 3x3 determinant. It's that same formula, but it's specific. You'll note we started with ijk here, which has to do with vectors, and then a, b, c, d, e, f are actual numbers of whatever. But cross product is a super important concept in math and physics especially. So just thought I would throw that out there as a possibility of something that maybe you've heard of. I never understood a lot of the calc stuff you're running about. Well, that makes sense because you're not in calc. I teach calc and I don't even understand the calc stuff that I rant about. So, you know, whatever. But anyways, eventually, if one day, whether, you know, in your current physics class or a future physics class, you'll probably end up talking about a cross product more. And depending on what math classes you go on to take. And a cross product is just it's a 3x3 determinant. But we just kind of apply it a little bit differently, but the formula is the same.